Despite humans are very small, even just compared to a galaxy, we are still considering the great amount of energy of a macroscopic system, because at the fundamental there are particles and atoms anyway. Since at our dimension we approximate trillions and trillions of evolutions for every present, the fluctuations of energy at macroscopic scale are often so tiny or less persistent to cause only subtle variation in the total energy. And when we can no longer measure transformations or displacement of energy, to us the time isn't running anymore. Usually this immutable is just appearance. The system is not static, but events are unfolding on a completely different scale. Two realities can be apart because of space, or because of different spacetime, both by gravitational potential. Then dealing with meso and microscopic, systems are far away based on how spacetime evolves in each locality. We can simplify the bigger one with general relativity, when the different rate is because of gravity, while in the very small, relative motion is affecting time according to special relativity. But here the high velocity of SR must be considered together with small sizes and the tiny amounts of energy involved. Both places are different spacetime compared to the humans one, so relativity is contributing to what we perceive from them. Temperature, as example, is a massive number of interactions and energy exchanges. Here we usually consider chaotic demotion and statistical devolution of the system. When finally events becomes difficult to distinguish, the arrow defined by thermodynamics disappear. Anyway, even isolating one stable atom, there will be fluctuations. But if a system is not evolving, from the outside, it's like the fluctuation doesn't even exist. As example, the electron may seem occupying the whole orbital, because to us this condition is equivalent to no time running. We realize, however, that it's just appearance when we try to interact with the particle. Each time the electron is found in just a narrow volume of its orbital, and the system has continuous electromagnetic fluctuations. Here, as example, an electron is trapped with electromagnetic fields, and while it's floating, we can see the spin flip. And here the G2 at Fermilab is testing for anomaly in muon spin. So even what looks stable can fluctuate, and we can't stop its space-time because fundamental movement keeps both in space and time. The apparent uniform derives from the distance in space-time and the relevance compared to total energy. Another case of undetected flow of time comes with decays. At our scale we can define the two states, not decayed and decayed. With 5700 years of half-life, roughly half of the radioactive atoms decay over this period. However, in this way, all not decayed are indistinguishable, despite just a fraction of them is about to transform. Decays can occur with consistency only if every atom keeps accumulating. This can explain the halving. Even what from our scale may look still is evolving on its own course. All not decayed can look alike, but each one keeps accumulating spacetime. Otherwise we can't have the macroscopic coherence of the half-life. On planetary scale, with GR we see that gravity affects the flow of time. Just as the same mass on the Moon weighs much less, time runs slightly faster. Gravitational potential can slow down the flow of time, affecting the rate at which events occur. Our clock is counting oscillations. Here we need about 33,000 of them to get 1 second and quantize continuity. Different gravitational potentials change speed at events and affects the oscillations in space-time we use to define local time. On the Moon we count them slightly faster than on Earth, and the gap grows over time. None of the two, however, can be considered the true time. We are just relating two of the uncalculable rates of the universe. We can take as many frames as we want, but there is no absolute value. Each one measures its own reference for 1 second. The different rate of time is thus impossible to perceive locally. Whatever the gravitational potential, all space-time look the same. In fact, because of consistency of physics, within every locality, just like the clock, everything else too has the same behavior of the quartz, and the effect of gravity on the flow of time is not locally detectable.
How about that?
The relativity we measure comes from just the difference between spacetimes. But we need to accumulate, then compare, to notice the gap and how physics is coherent inside relativity. Everything is inevitably moving with the same direction, and within each locality, the rate of spacetime appears the same. The only thing we can notice is the difference in a comparison, and so we realize the relativity with each one having its own rate. These macroscopic effects originate from the speed of fundamental interactions always running in spacetime. Moreover, the locality of particles deriving from the confinement allows for recursive fluctuations that don't take the particle anywhere and give the system inertia to conserve momentum. So, since we memorize the past, even when the system is not evolving or cumulating, we can abstract the direction in spacetime. Fields, on the other hand, can evolve, but they don't have their own entropy. All properties and variations come from the particles emitting the field and interacting. The same with light. Lacking interactions with particles, it can retain its quality indefinitely. We can usually identify the flow of spacetime considering the dispersion and the typical loss of amplitude over distance. If this light wave could represent some instant on Earth, the image will propagate frozen in spacetime as the single frame of a movie, but it gets weaker and weaker, losing details and becoming an ever-increasing blurred image. However, light doesn't have proper entropy or time, because as with momentum conservation, waves don't change qualitatively. So inside the image, the original waves could still be there after millions of years. We can draw an arrow in spacetime, looking at how light propagates, but such waves cannot evolve on their own or affect each other. Their entropy in time is always coming from particles. Direction of spacetime is instead easy to spot in irreversible processes. They are unidirectional, so you can maybe get another one, but you can get the first back. In these processes, some piece of additional value can be lost. Despite we keep conserving energy, there are abstract properties or informations that cannot be recovered. It's possible because they don't have a physical counterpart, so they don't affect evolution. Draw a bucket of water instead of gasoline doesn't change the flammability, thus when I burn the paper, the content is physically irrelevant. Only the mind lost some additional meaning. It's something we can elaborate, but physics doesn't care to preserve because it doesn't affect interactions and transformations. And it couldn't be any other way. These informations are subjective. A message can be misunderstood or hidden between the lines, and a detail can be lost. To us, the same amount of energy can carry different amount of informations and history. There is no physical logic in these values, yet physical laws are still a thing. And this is where all the fun of information theory begins. Informations and irreversible processes are useful for those who can memorize and elaborate, but physics exists only in the actual. There is no place to store all versions or the arbitrary amount we can imagine. What we can find in each present is just physical traces of the past. With Einstein, this arrow can run at different paces based on the gravitational potential. Each of these macro arrows represent large areas with uniform potential, but they are still abstractions with no exact counterpart in real. They are the approximations of gazillions of systems and interactions. As the macroscopic fluctuations of energy becomes negligible, so the macroscopic relativistic effects are not perceived. And we can share large space-time where events look synchronized with respect to the speed of light, but it's not real simultaneity. It's just the apparent common error of space-time. In closing, before causality, to prevent time travel, it's the lack of a single time through which travel. We can mix all together in one reality, but there is no highway to ride back and forth. Spacetime and entropy derives from particles, the only form of energy capable of defining the changes which we interpret as the flow of time. So even if we can macroscopically separate space and time, and as example using coordinate you can move forward and backward in space, the fundamental level possesses an inseparable space-time, thus events always cumulate and set their direction. Some of the space-time can be far away from each other, with time slower or faster based on the relative point of view, but it can't stop because physics is locally always the same. Altogether, human can witness something the painter can't even comprehend. Timeless journeys and countless histories, cause everything in the universe is running its own present in space-time.